Very good morning, and I have great pleasure in welcoming all of you to this online webinar organized by the Department of Mechanical Engineering, Francis Xavier Engineering College, Tirunelveli. I am Dr. Samuel Ansel, professor in the department, and I would like to present before you a brief profile of our campus. Francis Xavier Engineering College is located at the heart of the city Tirunelveli in the state of Tamil Nadu, a college that is heralded worldwide as the Oxford of South India. Our college was established in the year 2000 with a vision to provide education in engineering with excellence and ethics to reach the unreached. It has been conferred with the autonomous status for a period of 10 years with effect from 2019 to 2029. It has also been awarded gold category by AICTE CII survey and Industry Link Institute in the year 2018. We offer 6 UG programs, 10 PG programs, and more than 4,000 students are pursuing their degree in our campus. The Department of Mechanical Engineering is the largest department in our campus with around 700 plus students and 30 plus faculty members. Our department has been supported with good infrastructure and excellent lab facilities. Our department has been accredited with the National Board of Accreditation. Apart from regular academic activities, our students have been trained and imparted with various skill training programs and value-added courses. The special feature of our department is the establishment of 3 applied laboratories in addition to the regular labs. The purpose of these applied labs is to inculcate students with innovative skills required by the industry. The well-defined objectives of our department with its collaborative teamwork enables each and every students to march towards the college vision. Thank you, and once again I welcome all the viewers for this session and hope we will have a productive time. Thank you once again.
Good morning to all. I am very happy to introduce today's resource person, Dr. Eriki Ananda Kumar. Presently, he is working as Associate Professor in FTVT University, Ethiopia. Previously, he was a Faculty of Mechanical Engineering in Caledonian College of Engineering, Muscat, Oman. Also, he worked in Nila University and Seji University, Malaysia. He has more than 15 years of experience in research, academics, and industry. He has published 2 different books. The first one is Predict the Ball Bearing Fault, and the second one is Crack Propagation in Spur Gears. Also, he has published more than 30 papers in reputed journals and in different conferences. He received his BTech degree in Mechanical Engineering from Jawaharlal Nehru Technological University, Hyderabad, and ME CAD from Satyabama University, Chennai. He has finished his PhD in Automotive Design and Manufacturing from University of Newcastle, Malaysia. His research area includes titanium alloys, nanotechnology, simulation, modeling, and analysis. He is actively supervising the undergraduate, postgraduate, and PhD students in the area of mechanical and automotive engineering. He is a member of different professional societies. He is also the advisory committee member and editorial committee member of various reputed journals. Now I am inviting such a wonderful personality to take this session. I welcome you, sir.
Hi, good morning, all. I'm Dr. Eriki Ananda Kumar. I'm working as associate professor in FTVT University, Addis Ababa, Ethiopia. So today I'm going to explain the machining of titanium alloys using various technologies. How you're going to be, for example, titanium material is very expensive and also very difficult to machine. So how we are going to do this kind of machining is now. I'm going to explain using the different technologies means turning operations, milling operation, grinding operations, different types of technology. Now I'm going to various technology. We will start from the turning first and how you get the parameters and milling and grinding operation. If you see here, my main objectives, slide number 2, please. Yeah, in this one, see the objectives. The titanium alloys are extremely difficult to machine and economically it's very expensive. So that to minimize the machining cost, using novel bondless diamond grinding wheel, analyze the performance of nanometric finishing of grinding machine. That means grinding machine, so using the parameters of grinding, so how you are going to do the operations using grinding machines. So here I'm going to introduce one tool that is bondless diamond wheel. We'll explain to you later one by one. And the next one is that is grinding operation area. And coming to the milling operation area, while machining of titanium alloys, the cutting zone temperature is too high, so that its reduced temperature cutting zone is favorably changes to milling operation. So that means what? In this case, the workpiece metal it became give the temperature. That means it gives some temperature became hotter. So then what happened? The material gets softened. So automatically you can get remove the material. So that comes to my technology applied in the milling operation. When coming to the next operation is turning operation. In this case, thermally conducted very poor, the titanium composite. Therefore, during machining is a heat generation and dissipated so fast at the concentrate of heat part edge cutting tool edge. That means what we are going to use a single point cutting tool in this area. So the analyze the performance of turning operation clearly. So before we are going to do this kind of operations, first of all, you should know the parameters. So the parameters, what kind of parameters we are going to use is, you should know the type of material. Is a grade 2 material, grade 5 material, what kind of titanium material you have to be choose first of all. So of course, different grades or different alloys is there. Now I am going to use grade 2 and grade 5 combination, sometimes grade 2 material as well as grade 5 material and sometimes combination of materials. I am going to do the machining parameters. We'll see here first the parameters of the titanium. Slide number 3 please. Yeah, you can see the parameters of titanium elements here. The modulus of elasticity in the titanium element is 107 to 114 gigapascal. The atomic weight is 22. Melting point is 1668 degrees centigrade. The high and the HCP is the one crystal structure is with Poisson's ratio 0.34 Poisson's ratio. The thermal conductivity here I mentioned 6.7 and specific heat 610 joules kg Kelvin and shear modulus is 45 gigapascal with 0.068 ionic radius. There is an atomic radius also 0.14. So should we know the limit before the whoever do the researcher, you should know the parameters of the material, either titanium, MS, whatever it. But first of all, once you have to know the materials, the properties and parameters and the material, then we have to easily to start melting point and based on that we have to be start the one. And first here I have to mention some problem statement. What kind of problems we are going to face in these titanium elements? Slide number 4 please. In this slide number, in this problem statement, you can please clearly you can check there what kind of problem I'm going to be solve here. Machining or high cutting temperature rapid tool wear. In this case, to minimize the tool wear, currently the machining of cutting speed less than 60 per minute. So this is one kind of problem. And the machining characteristics of titanium alloys are poor thermal conductivity. The heat is concentrated on the cutting edge and tool face. The second point is tool alloy has a strong, it's because tendency, the chemical reactivity cause welding along with the rapid cutting tool failures. So in this case, the tools of failure coming keep on. And the third point is heating induction method. So in this milling procedure, I am going to introduce this kind of one kind of method. This is a heat induction coil method. Has to be found of promising results machining of mild and hardness steel. Hence, investigations of the effectiveness of induction heat method, that is heating method on the improvement, the titanium wide range of current speeds are also needed. In this case, what kind of mill? I am going to, while machining of the milling, so I am going to the workpiece with help of induction coil, I am going to increase the temperature. So automatically the material will be softened. If material will be softened, automatically what happens? So the cutting tool will be easily to cut. But of course, the temperature will be transferred from job to tool. But doesn't matter. We are going to be concentrated on the machining parameters only. That's all. In this case, if you see that my turning operation, the slide number 5, please. If you see that grade 2 composite, I'm going to concentrate the turning operation grade 2 material. In this case, my workpiece and tool inserts, the chemical compositions I mentioned already. In this case, the turning, how we are going to operate it. So keep on. So in this case, the turning operation, we are going to be using CBN boric nitron tool. So in this, what is that? So boric, boron nitrate, cubic boron nitrate. It's a super hot. It's a hottest known material eligible for the ferrous materials. And our CBN is very expensive and only available in the form of simple spec shaped inserts. It's a simple shaped insert. It's not very difficult to run. And series of cutting operations upon CBN is titanium cutting force, chip formation, surface finish, etc. And for this performance, the investigates the effective of cutting speed and the rate of using some of the inserts. It's a good surface finish will be 0.1, 0.5 to 1 microns was obtained for cutting speed between the 15 to 45 meters per minute. The feed with the 0.1 to 0.2 mm per revolution of the cutting after 1 meter. This is the one. And to find the stress intensity also is one of the one of the advantage for this. And also this one, find the tool we are doing the mission built titanium alloy lathe using CBN cutting tools comparing the actual tool near with the illustration. That means polycrystal diamond PCD insert. That means I will explain in my last but one slide. I'm going to comparing with that PCD insert with the WCCN insert. So I will explain that one. So slide number 6, please. So in this case, how the operations will be done using lathe machine, cubic boron insert, various sets of cutting speed, feed, depth of cut. So we are going to change the. I told you already the parameters in between which parameters we are going to fix in limit between this limit. And during reinsertion of the tool insert after every wear measurements, inserts were placed into the slot made the tool holder, the tool overhand, and flank wear measurements have to be made in this measurement, the surface of work pieces. And while see this, my graphical representation. 7, please. Slide number 7. Slide number 7, please. Yeah, the graphical representation. The spectators clearly, please observe clearly here. They mention speed 9, 60, 90, 120. I'm going to fix the speed parameters and 60, 90, and 120. In this case, how the flank wear and how the machining time you can observe in this point. Depth of cut 0.05 and feed is 0.1. In this case, how the depth of variations of flank wear with machining time for depth of cut 0.05 mm and feed 0.1 mm revolution, you can see the point how it reaches. That is what? And 5 minutes, the machining time at 5 minutes, so what is the flank wear? It comes 0.05 mm. And if you see that 10 minutes, then how it is? So you can see that the blue color one is 60 speed. And the pink color one is 790 speed. And then light blue color is the one, the green color, it looks green color is the speed 120 speed. So in this way, the RPM, how could be? If it is 60 speed, how it elaborated? See the one, after coming to the 30 minutes, it reaches 0.4 mm. So while coming to the same, the speed is increasing 120, that 0.4, that is 0.35 reaches within within 15 minutes only. That means what? If the speed is varying, automatically what happens? The flank wear also will be changed. That is my experimentally again I want to show here in this case. For example, not only this experimentation, I have to check with some of the source with other source, the comparison. Slide number 8, please. The configuration of longitudinal bar turning experiment force results. You see here the force, the insect how it will penetrate it, and the cutting tool how it should be. So in this case, the uncoated tungsten cobalt carbide (WC), you see here tungsten cobalt carbide uncoated and titanium coated. So here CBN coated, CBN with the titanium coated combination. So here the source from one of the gel ethyl. So he mentioned force per the rate. Here I mentioned with the uncoated how, titanium coated how it is, and if you comparing this one, the CBN coated between is very high, the speed. The velocity is equal to 100 meter per minute. So in this area, we are going to be what I'm going to explain here. So depends on the insect coating. Automatically, you can get the performance, and it will be change the results automatically. So in this case, what we have to do the experimental work with the various cutting parameter considerations, specific work how the cutting tool shank size 12.5 to 12.4 in between. The cutting speed 60, 90, 120, the speed is 0.1 to 0.3. I can change frequently in this depth, and depth of cut is 0.05 to 0.15 and 0.3. So we can change accordingly to get the fine finishing. So until that, you can get it here. And while coming to the procedure wise, here in this case, I'm going to find some 18 page. That means I'm going to extend now, do the exercise with experimentally 18 parameters. I can change 60, 90, 120. The depth of cut is 0.5 to 0.1 to 0.3. Feed I change 0.1 accordingly. But time sense is changing 69.2, 67.8. So about based on that, I can get this result. So what I'm going to explain here is the change of the timing, speed change, timing also change, the flank wear also same. So it will be show like that. So this is about for the titanium alloys using turning operation. While turning operation, so this is one of the tool we are going to use of different types of coated, uncoated, titanium coated, and CBN coated. CBN with titanium insert coated. So these kind of combinations we have to be get all the results is different and different fine finishing. So coming to the grinding operation, I'm going to just briefing the grinding operation, how we have to do this one. Slide number 9, please. So in this grinding operation, I'm going to first of all fix the speed of the grinding wheel 5000 RPM to 8000 RPM. Yeah, it's very high, but we are going to get the fine finishing in this area. At a speed of 5000 RPM, the diamond wheel with stainless steel shaft worked well when machining titanium. When the speed was increasing to 8000, that is from 5000 to 8000, the wheel with the carbide shaft worked better. Rigidity of the grinding wheel was improved. You can see in this graphical representation, I mentioned A and B. This is one kind of novel boneless tool. It's made from Malaysia. So one of the professor, V.C. Venkatesh, he has to be found. He has to be found this kind of invent a kind of grinding wheel to get the fine finishing of this one. So for example, I am going to make one kind of experiment with the 20 mm thickness of titanium slab. Slide number 10, please. You can see my students or spectators. Please check here. The 20 mm titanium alloy slab is mounted on the surface, and then it clearly observed it got some arrow mark. In its arrow mark is that is novel boneless tool with a different kind of material with the stuff, the shaft. So after that, the down you can observe clearly the workpiece is there. Some impressions also available. Impression 1 and 2 and 3 and 4. Some impressions are there. That impressions I will explain the speed of difference 5000 to 8000. While coming to here, the experiments high speed of carbide shafts could not be conducted as a supply for special services did not deliver in this report. So just I want to show for outlines only. However, the low speed of carbide shock well form a point of view surface is a 0.2 micron anomaly when used the emulation based on water coolant. So sometimes you are going to use LN2, the coolant. So liquid nitrogen, that means what? Either dry and wet surface. So I'm going to comparing both the dry and wet surfaces. Here I'm just explaining the dry surface, dry environment only. So coming next point, experiments at high speeds with carbide shock conducted low speeds of the carbide shock perform well for the point of view of surface roughness is 0.2 when used with English water based. This is good surface for the good surface purpose. So this is one very important. So in this case, I want to explain clearly the grinding how you're going to do the cryogenic. So I told you that dry and wet surface. If it is dry surface, how it is wet surface. To analyze performance of nanometric finishing, the nanometric finishing for grinding operation we are going to use. And also to minimize the cost using novel bondless diamond grinding wheel, use this kind of diamond wheel so we can reduce the cost. And to state the performances, how the performance, the one. Right. And then in this case, liquid nitrogen you are going to use to finding, that means during cryogenic grinding, the finish was not so good. And the cutting force were high due to elevated of hardness of titanium during high speed with the carbide shock conductor. So that is, I mentioned here how many grounds. If you see my presentation, 1, 2, 3, 4, 5 grounds I done. In these 5 grounds, for example, the 20 mm thickness with the 14,000 RPM. So how it is means 5,000. First of all, I mentioned 8,000 RPM with the feed 0.1 with liquid nitration, and 5,000 RPM with the feed 0.1, and you can see the different comparisons of that piece. So that is the one. So in this case, how my analysis of experimentation for the is conclusion, the bondless diamond wheel machining of titanium with conventional coolant white gun. The applications in this case, bonded grinding wheel, which is another super abrasive next only to diamond, results in increasing the force and wear. The applications was LN2, everyone LN2 is a coolant for using the investigation purpose. And also LN2 grinding, a novel boneless diamond wheel has shown the significant success of the term of improved surface finish and research as well as project for precision tolerance. And coming to the slide number, next slide please, slide number 11. In this one you see that after grinding finishing, how my results, graphical representation of grinding, carbon dioxide has certainly lengthened to life. However, surface finish was not improved and the grind force was not reduced. The tangential, I'm just mentioning the tangentially how we can do. It's longitudinally and tangentially how we can do the one. If you do the tangentially, how much my force and the newtons from 10 to 0 to 80 newtons I can make, and the minutes is 0 to 35 minutes. If it is making the 0 to 35 minutes, for example, my force I'm going to apply the 40 newtons within this 1 minute, so how my performance. If I'm increase the 2 minutes, so automatically the force should be increases. So this graphical representation will be explained. If coming to the minutes of 10, but my force is 10, I can get the good surface finish here. So this is the one experimentally I can done in the what is the grinding operation. So this is the part of grinding operation using the titanium. So before that, turning operation, how and with help of CPN inset and the grinding with help of lower bond. That means the two parameters, that means two operations, turning and milling, I just concentrated focus on the tool change. There is no work piece change, means work piece changing parameters. Work piece is constant something like. But while coming to the milling operation, next slide please. Yeah, while coming to the milling operation, I'm going to focus on workpiece also here. The workpiece I'm going to introduce preheating technology. That means induction heating method and atmosphere environment, means room temperature. So while coming to the machining in this area, tool material technologies advance rapidly, enabling meaning a difficult machining material. Means how you are going to be remove the machine high removal of cutting speed performance. So in this case, the point two is higher speed and removal rate using improved productivity. Predictable tool performance is essential when machining tool is computer control is operated in interaction. The long tool life is desirable, especially when machining can automatically or place in a cylinder system. But coming to here, my explanation in this milling operation. Of course, everyone says titanium material for milling operation better. This one I will explain to you later. The one. Well, coming to titanium analysis, this is strong and difficult. We are going to because the tensile force is 1400 megapascal. So in this case, the machining operation, I'm going to introduce here VC 450 spinner, the vertical milling machine, and additionally where WCCO, that means uncoated tungsten carbide, cobalt carbide, and polycrystal diamond. I'm going to use the two types of inserts. So how the performance using two kind of inserts with preheating technology. In this case, inserts fixed at a 25 m distance across the mill and comparatively examine the effect of preheating temperature on machinability parameters. So that means tool life, surface smoothness, and force of cutting. The impact of preheating on the surface irregularities, chip, morphology, we are further investigated. That means here is a composite design, focal point composite design, RSM, response of surface methodology. So join to make test model, the tool life, cutting force and force orders, both room temperature as well as preheating machining method. So I will explain both how the room temperature, the performance, how the preheating performance here. So in this case, so the both room temperature as well as preheating method, the product was furthermore used for support to the tool life and surface unevenly by streaming the cutting parameters on preheating temperature. That is the executions of uncoated that tungsten cobalt carbide was greatly implemented. Is directly around implemented times of different relations of room temperature. Even the estimations, that means the estimations of the tool life are essentially higher than those cutting of PZD. That means this is polycrystal diamond under room temperature force extended tool life. In addition, preheating machining method extended chip device contact length, chip serration, realize the reducing of equipment wear rate. Of course, the product which additionally uses the boost of tools life of in the simulated surfaces, streaming line, the cutting parameters, preheating temperature. So these are all commonly welcome. But what I am telling is the finally the preheating method are executed of uncoated tungsten cobalt carbide was massively enhanced. Also, the estimation of tool life are significantly high with PCD under room temperature machining. So preheating machining significantly adds on reduction of work. As a result, force cutting encouraging expanded tool life. So that means preheating machining encourage extend chip tool contact length, stable chip serration, show to reduce the tool wear. So that means what my conclusion, my explanation here, they have using some material, that means what is it, alpha beta combination. The tensile force is 947 to 1000 megapascal one. So you can use this high strength material. So what is that? Two type of material you are using is carbide sintered, that means uncoated tungsten cobalt and polycrystal one. And in this case, you can see my, what is it, next, please, next slide, please. Slide number 30. Yeah, you see this picture with the room temperature. The spinner VC 450 milling operation, with the machining under room temperature and preheating. Have you observed the down one? If room temperature is normal, machining parameters I'm going to use here. Well, coming to preheating condition, you see here the down one picture, small picture, the preheating condition. Sorry, the spelling mistake condition, CON here. Condition. Here, they got, if you observe that two coils are coming to touch the workpiece. You clearly observe that is point number 5 and point number 4. The point number 4 and 5. Point number 4 is the heating induction coil. So using some special device to get the temperature to make the workpiece getting the temperature. So that means what? Here I am going to use preheating methodology. So preheating methodology case, the help of preheating condition, the test of conductor means the complete setup. You see the picture number, the small picture, when you get a point number 4 and point number 5. The cutting conditions are a rate of wear of record with different intervals with the transfer. Here 250 mm. 2 failures and wear was recorded with the help of microscope. Flank wears not more than exceeded 0.35. So as per room temperature, preheating conditions the tool life has predicted in inside. Uncoated tungsten cobalt carbide as well as PC polycrystal diamond. So the parameters of cutting speed, depth of cut, speed and RPM I just mentioned 10 experimental series. So in this 10 experimental series, so I can get a different variations of preheating conditions. One parameter has to change the temperature. That is, all iterations RPM shows have different properties. It has to be recorded with the help of microscope. And the 2 inserts is developed that the feed has to more than significant influences on surface toughness, space of the cutting and depth of cut. Effect between those parameters has more effect to roughness value. So that is why here the built-up edge, the chip condition, the built-up edge, room temperature and preheating serrations segments more reactive with chemical. And if coming to that picture is even the room condition. You see that the spinner mission DC 450 and I'm using that mission. The mission under room condition, the tool life, surface roughness and cutting forces end milling of titanium uncoated PCD is respectively under room temperature is a condition 250 degrees. Sorry, 25 degrees. Within 25 degrees room temperature means of course the workshop getting some air conditioning workshop. So that air conditioning workshop means so automatically it became the temperature is 20 to 25 or sometimes 25 more. That's it. So in this case, including the feed rate, so I'm going to maintain the 25 temperature to get in the workpiece machining parameters. So in this case, I'm going to find out cutting speeds 40 and 125, 70. So I'm going to take randomly that picture. In this operation or conductor depth of cut by 0.6, 1 and 1. That means I choose 3 parameters 0.6, 1 and 1.6 parameters for uncoated. The speed is 485 RPM, maximum speed is 2550. That means I have to vary. So the minimum speed is 485, the maximum speed is 2000. So I can just maintain this one. The fix of depth of cut is 0.6 and 1.1, 1.65 with the parameters to run the tool PCD inserts. And minimum speed is 1300 RPM and the maximum speed is 3000 RPM. So please you have to concentrate here using uncoated. That means WCC uncoated tungsten carbide 1 speed and polycrystal steel is another speed. So that means the PCD is I maintain the temperature speed is 1300 to 3000 RPM. But uncoated, I'm going to use 485 to 2550 RPM. That means what? This range of speed is low and PCD is very high. That means this is uncoated one. This is polycrystal diamond. This room temperature machining to increase the cutting parameters. And it's a decrease in the two life end milling with the both inserts. So I'm going to take the operation, the 5 to 8 operations. After this, the cutting parameter varies of RPM, WC, PCD respectively. In WC, that is a tungsten cobalt carbide tool, the insert, the maximum RPM to reaches 2500 to 2550 without affecting work surface, whereas PC. That means what? After the speed increasing, the workpiece is affecting. So that means what? Already the temperature you are giving more and more certain temperature to the one. I'm talking about the preheating condition. So in this case, that uncoated insert reaches 2550 temperature. And coming to PCD, the maximum RPM beyond the uncoated insert, that means what? It crossed the 2550, it reaches more than 3000 also, the workpiece doesn't affect anymore. That means the design results is experimented 2 lab surface results according to end milling, uncoated insert, how the condition tool lag is sharply decreasing with an increasing in cutting speed, irrespective of whether machine is conducted. So, yeah, this phenomena may attribute to the increase in the shear zone, maximum tool, and the cutting zone. So, if you see that graph parametrical, the data of cutting forces, next slide number 14, please. So, if you see the graph representation, the data of cutting tool during the machining and the room temperature and pressure, and increasing in axial depth of cut and feed leads to increase in cutting force, where an increasing in cutting speed decreasing the cutting force. Please make sure here. That means where an increasing the cutting speed decrease the cutting force. That means what? Increase the cutting speed automatically, the force is decreasing. In this test, the cutting speed significantly reduces the result cutting force, while feed is substantially increases the result cutting force. Also, the axial depth of cut increasing the cutting speed is cutting force accordingly. The average surface toughness data of end milling with the PCD under room temperature conditions are indicated that increasing in all the cutting force. In addition, this point is drop the tool life is also related to high wear temperature increases. So, what I'm going to explain is end milling operation were conducted with preheating zone. In this case of temperature function, preheating zone is the main function is temperature. So main function is temperature. Based on that, the cutting speed, both inserts temperature to be varied with 320 degrees centigrade first iteration, and just increasing the temperature 320 to 355 degrees centigrade, and 455 degrees centigrade, and 575 degrees centigrade, and 655 degrees centigrade. Of course, please make sure I already explained the titanium material in the beginning of the slide I mentioned already. What is the temperature, the melting temperature of this titanium material I mentioned already here. The melting point is 1668 degrees centigrade. The first second beginning slides I mentioned already. So in this case, you make sure in that point of view, you have to follow the temperature. So based on that, I follow the temperature 320, 355, 455, 575, 655 respectively. So that we're increasing up to fine finishing purpose. In this case, parameter to run the tool uncoated insert, the minimum speed is 485 RPM, maximum speed is 2550 RPM. Yeah, guys, I told you already beginning. The speed is very low condition from the 485 to 2550 is uncoated. While coming to The PCD is more than, that is 3000 it reaches. So also fix the feed parameter feed rate. So 0.055, 0.065, 0.090 and 0.13 mm per tooth. Please make sure it's mm per tooth. If the parameter run the tool of PCD insert, minimum speed is 1300, but while uncoated tungsten one, the minimum speed is 485. But here, the PCD insert, the minimum speed is 1300 RPM. That is the change because this is PCD, that is uncoated copper tool. So once you can reach the maximum speed, when the fine finishing will be get, you have to check the speed. That is 2550 RPM. You can get fine finishing. So that means uncoated up to there. But in this coming to the PCD, not that much. It coming to maximum speed is 3000. So then only you can get fine finishing. So I can show that in the graphical representation. You see here, the uncoated and PCD, the feed rate, temperature versus current. Temperature versus current. This is one of the source from the Kumar. So he's mentioned this uncoated is like this and PCD. But while coming to my analysis, this is not uncoated is different and PCD is different. Of course, we can see the based on that temperature. We can with experimentation or conducted. Means 10 experiments or 5 experimentations, you can get it. Overlapping information, you can get 2 inserts. Cutting speed. That means for experiment PCD, we have selected lower than higher speed for experiments with uncoated carbide, tungsten carbide, cobalt carbide tool. Preheating temperature, determines the surface roughness, effects of condition of this. So here, feed increases. If feed increases, the surface roughness stable, where cutting speed significantly reduces. The surface roughness increasing and increasing the cutting speed and feed leads to decrease the tool life, whereas and increasing the preheating temperature, increasing the tool life. The effects preheating on tool life is end mill with uncoated, both tungsten carbide tool as well as polycrystal diamond. So what I am going to be explain here, the tool life is depends on the cutting speed. Please make sure the tool life is depends on the cutting speed. Related parameters also with room temperature as well as preheating condition. For end milling with the help of uncoated, that means uncoated PCB, uncoated tungsten carbide and PCD inserts are given best results that our cutting speed is increasing to increase the temperature. That means what? If speed increases, temperature increases, we can get better results. In this lab case, both cutting tools and mostly the feed. What I'm going to final here, I want to give the explanation. Mostly feed factors are effect of surface surface under both conditions, in temperature as well as preheating conditions. So cutting speed, axial depth of cut and feed respectively, preheating condition has proved to increase the optimum cutting speed and increases metal removal rate. Subsequently improves the machinability parameters. Also, of course, which includes the tool life and decreases the cutting process. Preheating method is alternative. Is one of the alternative method machine critical method. For example, sometimes you feel how I can more and more uncoated inserts are going to be spoiled with minimum parameter with minimum surface finishing. So in this case, we are going to use preheating technology induction method. So in this preheating induction method, you see this graph uncoated and PCD here. What explanation here? Feed rate 37.3, and you see here the minimum feed rate we are going to use uncoated 37. But coming to PCD, feed rate 87. So accordingly, his explanation. Of course, it depends on the temperature. So he is going to increase the amperes. Automatic temperature will be changed here. But you may calculate it based on the cutting speed and temperature. But here he explained temperature versus current ampere. But my explanation is cutting speed versus temperature. In the cutting speed versus temperature, I'm going to start from cutting speed 0 to until 700, and temperature will be increases keep on. I mentioned already how much the temperatures I mentioned. I started from there, right? So coming to that slide number 16, please. Last one, summary one. So I'm going to sorry not slide number 15, please. The conclusion. So finally, I'm giving the concluded on this one. When depth of cut increases the sheets, flow out is lengthy and fall. Lower depth of cut is sheets or in powder form where get increases as depth of cut increases. A good surface finish is 0.5 to 1 micron was achieved for cutting speed 50 to 40 meter per minute. Feed rate is 0.1 to 0.3 mm per revolution and depth of cut is 1 mm. So, dear spectators, I want to explain this good surface finish. I got it with help of depth of cut is 1 mm with a feed of 0.1 to 0.2 mm per revolution. So I can get good surface finish with that one. And slide number 16, please. In this case, I'm going to totally conclude the summary of using turning operation, grinding operation, milling operation. While coming to the turning operation, what my summary of conclusion on this one, the bondless diamond wheel machining titanium alloys with conventional coolant quite well. If that is conventional. If it is bonded grind wheel made carbon boron nitride, which is another super abrasive next only to diamond, results increasing of force and that I explained already. And coming to the next bonded wheel. So novel bondless tool. The bondless diamond wheel machine, it should be ordered for this tool. It's not available now. So you order this tool, you can use this kind of bond tool and you can machine, you can get fine parameters. This is that is very high strengthened tool. The bondless diamond wheel machining titanium alloys of conventional cooling well, bonded grinding. So same. This is another super abrasive next only to diamond. That is next to diamond. This is this abrasive resulting in the force and wear. And coming to the milling operation. So here I'm explaining preheating machining. The preheating machine substitutions suppress is a vibrations, starter, lowering the bounce effect, acting on the cutting tool and thus reduces the tool wear rates. So that is what, if you're going to take any kind of technology, alright, last slide. So if you're going to find any kind of technology, so you have to check either tool or workpiece. So you have to implement the parameters in the tool side or workpiece side. So what happened? So which is the perfect? Which one is perfect? For example, my analysis in the milling one, I am not focusing concentrated anything, not much more. Only two tools I am using: uncoated tool and PCB tool. I can just start the performance with help of room condition, atmosphere room condition temperature and room temperature, as well as preheating condition. So we can check. I can get this kind of. So we have to choose this kind of tough materials like titanium is very difficult to machine. Of course, nowadays still research is going on grade 2 material and grade 5 material. So these are all kinds of you have to be survey for this one. And in this machining of grinding, we are going to focusing first of all the speed. So what type of speed we are going to be reach? So sometimes it's automatically that bonded tool is very expensive. It's nanometric bonded tool, and cryogenic bonded diamond grinding of titanium alloy is an excellent surface finish in the nanometric range at low speed. So that what I am to explain that diamond is very expensive. So we have to be the parameters to choose simultaneously. Then only can get good surface finishing. So this is my presentation on the titanium machining. Is a titanium alloys machining using different technologies. That means either turning operation, milling operation, and grinding operation. So of course, still milling operation researches are going on with the preheating temperatures more and more. We can do more research on that. We can get good parameters also. So this is the yeah my conclusion on this one. So thank you for listening. So if you have any questions,
The first question from Mr. Matthew. Hello? Are you able to hear?
yeah, yeah,
First
yeah,
question,
please,
Mr.
you may.
Matthew. So he is asking, what is the coolant used in titanium machining?
LN2, liquid nitrogen. Liquid nitrogen is the best coolant for getting cryogenic. Liquid nitrogen.
Okay. So the second one is Mr. Dinesh Babu. Dinesh Babu asked that what are the demerits of titanium which needs to be rectified for implantation?
All right. Yeah, good question. Nowadays, the titanium materials they are going to use the medical sciences also for that dental and bones for that one. So in this case, so we are going to be find the new parameters because the titanium is corrosion less. That means what? It's a corrosion resistivity also, and also it's very high and tough material. It's a very high hardness material. That's what difficult to machining. If you want to do the application oriented for dental or aerospace, something like that, but the problem is the ore material to get the machine. So that is what our session is to using any means either turning or milling or grinding. So we have to follow this kind of technology. We can get good means we can get that parameter we can get that fine finishing and fine parameters to modifying the material as per the applications, either aerospace applications or dental applications or any other applications, doctor.
Okay, sir. The next question by the same Mr. Dinesh Babu.
Mhm.
What are the problems faced in titanium-based implants?
Yeah, while do the machining the coolant is very dangerous. So while using the coolant, it's automatically minus frozen temperature we are doing. So in this case, so I face this kind of things while applying that cryogenic liquid nitrogen. So after coolant, so we cannot see the surface finish. So it will take some time. So after again we have to do the machining and increasing the temperature. So these kind of problems will be occur. But it's not a matter if you take some time to finish up the parameters, fine parameters.
Then next question from Kandavel Kumaran Nadesan. So what are the applications of polycrystalline diamond?
The polycrystalline diamond, it's a expensive tool and it's a high what is it, RPM. For example, here I mentioned I just show the distinction between that uncoated one and PCD. The PCD is almost more than 3000 RPM also we can do the one. So the one is that is one of the big advantage for PCD.
Okay. So the next one from Mr. Vasanta Kumar. What about tool wear rates in WC tool, PCD and PCBM?
PCD.
Yeah.
Yeah, I mentioned the tool wear rule is very less in PCD compared to WC because the WC is automatically the started with the RPM is very low RPM. That means, but in the PCD, we can start from the high RPM. That is the comparison. If it is high RPM, you can use the same RPM to the uncoated. Automatically, the tool will be spoiled. But the PCD is not like that. That is the one. That's the reason the PCD is very rigid and very expensive.
Okay, sir. So one more question from Vasanta Kumar.
Mhm,
What will happen when we use cryocoolant in
mhm.
this operation?
Sometimes they are going to machining the titanium material uh, room condition as well as below the room temperature as well as below the room temperature. So that means what? While do the room temperature, the temperature of while machining, the temperature is transferred. The heat is transferred from workpiece to tool. The tool wear is more. The tool tip is spoiled. So what happens? That that tool we have to the tool tip.
The பைய ஓபன் பண்ணி கொடுத்துரு.
The tool tip will be increase the efficiency. For that purpose, we have to use the cryogenic. Only that purpose. It's not for workpiece purpose, that one. Because workpiece, we are already recrystallization temperature. Under recrystallization temperature, we are going to do the machining parameter. That's fine. But coming to the inside, we are going to, what is the tools? Life should be increased. For that purpose, we are using cryogenic.
Okay, sir. Thank you, sir. The next question from Mr. Sheikh Sulaiman. What is the maximum temperature of preheating of metals?
Yeah, that's what you see my second slide already. I mentioned parameters, properties of the material. First of all, before you are going to do any kind of research, any material, we have to check the properties of at what temperature it should be melted. So it should be recrystallization. So that means we cannot go that beyond of limit. Under that temperature, we can do any process, but depends on the tool supporting. That means what? The tool temperature also we have to check simultaneously both. If it is tool temperature is 1200 degrees centigrade and the workpiece temperature is 15 degrees centigrade, up to 1000 degrees, 1000 degrees also we can do the machining. It's not a matter. But we have to check properly the machining, fine polishing, fine machining is coming or not. If the surface finishing is very good, then no need to go for high temperatures. That's my analysis.
Okay, sir. That's all. There are no more questions from the participants. You are answered well. You are clear the doubts of the participants. Thank you, sir.
Thank you so much.
I hope you are all enjoyed this session very well and gain knowledge about the various techniques of machining the titanium alloys. First of all, I like to thank the resource person Dr. Eriki Ananda Kumar. He has immediately accepted our invitation and delivered a wonderful lecture about the topic in a well organized manner. Thank you, sir. I'd like to thank our students, Mr. Alban, Mr. Jason, Mr. Alex, and the team for supporting us, and the faculty members, Mr. Ebenezer, Mr. Sheikh Suleiman, and Dr. Samuel Hansen for their wonderful support to organize this webinar in a successful manner. Thank you, sirs. I thank our HOD, Dr. Joe Patrick, for his guidance and support for conducting this seminar. I thank the participants from various parts of the country, from various universities in India and abroad. I thank all the students and faculties participated in this webinar. I thank you all. Thank you.